Differential equations are notoriously difficult to solve, and there are only a few that you can solve analytically. So what I mean by that is like by doing hand calculus. Most of them you have to solve by basically estimating their solutions numerically or graphically, like we did with the slope field. But these are a subset of differential equations that you can solve by hand, and they're called separable equations. So, for the sake of time, and because I don't really think that this makes it any easier if I go over the abstract business, I'm gonna skip this. All you need to know is a separable equation is a first-order differential equation that can be separated. What does separated mean? Well, let's start with an example. Write down this differential equation. So dy dx equals x squared over y squared. We're going to solve this. Remember, a differential equation involves an unknown function and one or more of its derivatives. What is my unknown function here? That's right. Y is my unknown function. How do you know it was y and not x? That's right, because it's dy dx, right? We have the derivative of y with respect to x. So when we solve for a differential equation, we are solving for the unknown function. Namely, we're solving for a family of functions. And then if we're given an initial condition, we can narrow it down to a single function. All right? And that's exactly what we're going to do. So this is separable. And what I mean by separable is we're going to take the derivative and we're going to separate the differentials being dy and dx. Kind of like we do for u sub. So I'm going to multiply the dx to the other side of the equation first thing. So we're going to have dy equals x squared over y squared dx. Once you've separated the differentials, now your goal is to get any terms with x to be with dx and any terms with y to be with dy. So in this case, that's pretty straightforward. I'm just going to multiply the y squared over here to the left-hand side, right? So then I have y squared dy equals x squared dx. And now, to get rid of our differentials, we're just going to integrate both sides of the equation. So now, if I just throw an integral on both sides, notice that I have a complete integration operator, which is the integral itself, along with the differential telling you what variable you're taking the antiderivative with respect to. So on the left, we're taking the antiderivative with respect to y. On the right, we're taking the antiderivative with respect to x. What's the antiderivative of y squared? 1/3 y cubed. Now this is an indefinite integral, so I don't want to forget plus c. I'm going to call it c1. You'll see why here. So then the antiderivative of x squared dx would be 1/3 x cubed, and I'm going to say plus c2. The reason I do that is because it's plus any constant, and these two constants don't necessarily have to be the same, right? Now, with that in mind, couldn't I just subtract over c1? And if I did that, I'd have c2 minus c1 over here. Now, a constant minus a constant is still just a constant. Do you agree with that? So can I just call c2 minus c1 just an overall c? And so my point in doing all that is, yes, anytime you take a general antiderivative of an indefinite integral, you need plus a constant. But when you're using separation of variables and you're integrating on both sides, you only need to add plus c to one of the sides. and that will account for both of them. Does that make sense? So I just need to add plus c to one side. All right. Now my goal was to solve for an unknown function. What's my unknown function again? Y. So solve for y. Multiply both sides by 3. Oops. Y cubed equals x cubed plus 3c. Take the cube root. Y equals the cube root of x cubed plus 3c. And we're done. There's my unknown family of functions. There you go. That's part A. Part B gives us an initial condition. Y of 0 equals 2. Go ahead. You can. Absolutely. Part B asks us to solve for the initial condition y of 0 equals 2. So that's just going to allow us to solve for c, right? And go from a family of functions to a specific solution, one function. And so all I'm going to do is plug in 2 for x. Plug in 0 for x, plug in 2 for y, and then I'll have enough information to solve for c. So if I did that, 2 equals the cube root of 0 cubed plus 3c. All right, so 2 equals the cubed root of 3c. Cube both sides. 8 equals 3c. C equals 8 over 3. And then plugging that back into my function, I'm going to get y equals the cube root of x cubed. And when I plug in 8 over 3 for c, that's just going to give me plus 8, right? So Dylan, if you would have just said plus c instead of 3c, when you solved for c here, you would have gotten 8, and you would have still gotten this same exact function. Does that make sense? But you're absolutely right with that logic. You could have just renamed 3c as just c again. All right. So there's our specific function. So let's look at this in our slope field. So our differential equation was x squared over dy dx equals x squared over y squared. All right, so it looks like that. And our solution was, let's see if it'll let me plot just a single point. So we had the point 0, 2 there. I need a volunteer to come up here and try and draw in what they think the function's going to look like on top of the slope field. Oh, so many to choose from. Do you know what I'm talking about? What we were doing last class? Vincent, go do it. Go do it, and then I'm going to put the other one over it, and we'll see how close you get. Is it that scary to get up? No.
Wait, what do I do?
Yeah, no. You're doing it right. Don't worry about what I'm doing.
Oh. No, wait, I have 2 options to choose from here. That's kind of tough.
But it's going to go, like, look at overall patterns. Do you want me to increase the density? Does that help?
Uh-huh. There we go.
Okay. So let's see what our solution actually does. So we had y equals the cubed root of, what was it? X cubed plus 8. Don't worry, I still got to take the cube root. 1/3. Pretty solid. Pretty solid. So that's our single function solution there. And the slope field kind of represents the family of functions that we solved for initially. Does that make sense? Questions? Let's do another one. I don't want to do this one. Let's do one from the AP classroom. Ajay, do you have that one written down somewhere? Or do I need to log in? The first, let's do number one. I can't remember what, it was like dy dx and it involved e to the, okay. But write down this example. This is one of your AP classroom ones.
Mr. Teller, we can't see it.
Ah, thank you, Naomi. I haven't written anything down really yet. Oh yeah, thank you. Like that, right? Over e to the y? Yeah. All right, so this is one of the AP classroom problems. This is a separable equation. So first thing we're going to do is separate dy dx. So I'll do dy equals e to the x minus 1 over e to the y dx. And then I want to get e to the x, x terms with dx, y terms with dy. Constants can be on either side. Because constants, you can take the antiderivative with respect to either variable. So all I'm going to do here is multiply over e to the y. E to the x minus 1 dx. So once you have everything separated with like variables on either side with their corresponding differential, then you're ready to integrate. So all right, antiderivative of e to the y. Don't overthink it. It's just e to the y, right? Because the derivative of e to the y would be e to the y when we're taking y to be our variable. Equals antiderivative of e to the x, e to the x, antiderivative of -1, and then we don't want to forget plus c. All right, this was also an initial condition problem. Ajay, do you remember what the initial condition was? All right, so our initial condition is f of 1 equals 0. Now you could go through the whole process and first solve for y, but once you've integrated and you have your constant, if you're going to end up solving for that constant, you can do it at any point, and you might as well do it right now. Because if we're going to solve for y, we're going to end up taking natural logs, and we're going to be burying that plus c under a whole bunch of other operations, right? And so if we try and solve it after that, we're going to have to undo all those operations. Whereas right now, the c is just sitting there, right? So it might be easier to solve for right now. So I'm going to plug in 1 for x. I'm going to plug in 0 for y. And I'm just going to solve for c right now. So that gives me e to the 0 equals e to the first minus 1 plus c. E to the 0 is 1 equals e minus 1 plus c. And then we're just going to get c, add 1, subtract e. C equals 2 minus e, right? All right, so now let's go replace my c. Now I have e to the y equals e to the x minus x plus 2 minus e, right? No, I just isolated it on this side. So I just added 1, subtracted e. All right. So last thing, if I'm trying to isolate y, I'm going to have to take natural log on both sides, right? So I'm going to have natural log e to the y equals natural log of the whole right-hand side. E to the x minus x plus 2 minus e. And that just gives me y equals natural log e to the x minus x plus 2 minus e. And that's it. So maybe not the prettiest looking function, but who are you to judge? Not all functions just involve whole numbers, okay, guys? Some functions are messy. So that's it. I think that specific question asks you what's, Ajay, do you have it there? It's like multiple choice and it says, what is the value of f of? I think it's f of 2, right?
Yeah.
So it said like, what's f of 2? So at this point, you could just pop that function into your calculator and plug in 2 for x and it'll give you your answer, right? And then one of the multiple choice answers will match that. All right, so I want to do one more example. And this is called a mixing problem. And so these end up being differential equations. And they can be pretty messy. All right, so a tank contains 20 kilograms of salt dissolved in 5,000 liters of water. Brine that contains 0.03 kilograms of salt per liter of water enters the tank at a rate of 25 liters per minute. And the solution is kept thoroughly mixed and drains from the tank at the same rate. How much salt remains in the tank after a half an hour? All right. So that's what we're looking for. We're looking for the salt that remains in the tank. Now, that's changing over time. Because first we have 20 kilograms of salt in 5,000 liters of water. But then we're pumping brine that has salt into the tank, and it's draining out. So the amount of salt content in the tank changes over time. So it's a function of time. So we're just going to name it. I'm going to call y of t the amount of salt at time t. And what I'm looking for, let's see, everything is given in minutes here. And we're asked how much remains in the tank after half an hour. So that would be y of 30. That's what I want to know. How much salt is there in the tank at 30 minutes, right? Okay. Well, what they give me is a bunch of rates. They give me a flow rate in and a flow rate out, right? So the overall amount of salt that's changing, that would be dy dt. That would be the change in salt, right? The overall change in salt will be the rate that it's coming in minus the rate that it's going out. All right, let's talk about the rate that it comes in. Well, it's coming in at 0.03 kilograms per liter. So that's kilograms by volume, and then I need volume by time. And it's coming in at a rate of 25 liters per minute. So if I multiply that by 25 liters per minute, just doing a unit analysis, notice that liters cancel, and what units am I left with? Kilograms per minute, which makes sense. That's a rate of amount of salt coming in over time, right? All right, so multiply that out. What do we get? 0.03 times 25. 0.75. So salt's coming in at 0.75 kilograms per minute. All right, so now let's do rate out. All right, so the rate out, we don't know how much salt is leaving, but we named that. That's Y of T, kilograms, per the volume of the tank is 5,000 liters, right? And it's traveling out. So at any given time, there's Y of T kilograms of salt in the 5,000 liter tank. That's what we have there. And it's flowing out at 25 liters per minute, right? So the salt comes in, it gets mixed up. It has basically that potency, Y of T over 5,000 liters. And then it travels out at 25 liters per minute. And so if, again, we do a unit analysis, we end up in kilograms per minute out. Now 25 into 5,000, that'll reduce to 200. So this is Y of T kilograms per 200 minutes. So that's the flow rate out. All right, so let's create our actual differential equation now. We have dy dt equals 0.75 kilograms per minute, which is our rate in, minus y over 200, which is our rate out, right? All right. I'm just going to rewrite 0.75. That's 0.75, isn't that just 75 over 100? Minus y over 200. Or 150 over 200. Minus y over 200. And now I can rewrite the differential equation so that it's dy dt equals 150 minus y over 200, yeah? Everybody okay with that? And now my goal is to solve for my unknown function, which is y. So I'm going to separate my variables, my differentials, so dy equals 150 minus y over 200 dt. And then I need to get this to be on the side with dy. So what operation am I going to have to do to accomplish that? How do I get the 150 minus y over to be with the dy? Close, the other one. You're going to have to divide by 150 minus y, right? Because it's in the numerator. So if I divide by 150 minus y, that's going to give me this. So I'm going to have 1 over 150 minus y dy equals 1 over 200 dt. And now we're ready to take the antiderivative. So integrate, integrate. Let's work on the right-hand side first. It's a little bit easier. 1 over 200 is just a constant, right? What's the antiderivative of a constant dt? Or t in this case, right? It's 1 over 200t, and then we'll do plus c, right? Left-hand side, little more complicated. Gonna have to use a u sub. So over here, let's let u equal just the whole denominator, 150 minus y. Then du dy is just negative 1, right? U dy, sorry. Now du is negative 1 dy, but we don't have negative 1 dy. We just have dy left over to sub out for. So I'm going to move the negative 1 to be over with du. So negative 1 du equals dy. That means that integral on the left becomes negative integral du of 1 over u. Yeah. Why I didn't multiply by 200 here? I could have done that, but then I still would have had to divide by 150 minus y, and I would have ended up with 200 over 150 minus y, and that would have been fine. You would end up with the same function. You would have still had to eventually divide that over. All right, antiderivative of 1 over u is what? This is a special case. You can't just use power rule. Yeah, so it's going to be negative natural log u, which then replacing the u gives me negative natural log of 150 minus y. So there we go. Now I have negative natural log absolute value 150 minus y. All right, we're close, but there is an initial condition. There is a value that allows us to solve for c. Namely, they tell us how much salt is in the tank before we start pumping brine in. So that would be y of 0. How much salt is in there at time 0? 20 kilograms. So y of 0 equals 20. So like I said before, I'm going to solve for c right now just because it's already sort of isolated there. So I'm going to plug in 0 for t and 20 for y. And that's going to get me negative natural log of 130 equals c. Because 0 for t just cancels out that term. All right. So now I have negative natural log of 150 minus y equals 1 over 200t, whoops, ran out of room, minus natural log of 130. All right, and last thing is going to be to solve for y. So hold on. Negative natural log absolute value 150 minus y equals, shoot, what was on the right hand side? Oh, 1 over 200t minus natural log of 130, right? There we go. So let's solve for y. First, divide out the negative, right? And that's just going to switch the signs on the right-hand side. So I'll write that as natural log absolute value 150 minus y equals natural log of 130 minus 1 over 200t. How do I undo a natural log? Not multiply, but exponentiate both sides by e like this. Right? So now on the left, I just have 150 minus y. On the right, notice that I have exponents that are being subtracted here. When you subtract exponents, it's because you have a quotient of powers, right? So I can rewrite this actually as e to the natural log 130 over e to the 1 over 200t. And that's nice to do because what is e to the natural log 130 going to simplify to? This is just 130. And then I can also just bring this one back up to the numerator by negating the exponent. So 130 e to the negative 1 over 200t, right? Okay. Last couple steps. I can just add y and subtract that 130 e to the negative 1 over 200t, and I'm going to end up with y equals 150 minus 130 e to the negative 1 over 200t. There we go. There's our function for how much salt is in the tank at any given time. We wanted to know how much salt was in at time 30, so we'll just replace t with 30. This is going to be a calculator. So 150 minus 130 e to the negative 1 over 200 times 30. And I get about 38.108 kilograms of salt. That makes sense, right? Because you started with 20 kilograms of salt in and you started pumping more salt into the tank. All right, that's about as boss level as those separable differential equations can get. So good job toughing that one out.